Hello and welcome back. This is Jonathan Gardner. We're covering section 6.6. 6.6 has to do with congruences. It's a fairly meaty chapter, meaning that there are things in here that if you don't understand the previous sections, you're going to feel lost. So an important part of math is understanding what you've already learned. So there's two topics that I want to revisit here really quickly. The first topic is what we just covered in the last section, which is that isometries have some properties that are important. So first thing about an isometry preserves distances. Okay. So what that means is F is an isometry, then it's a mapping that if you take point P, let's say that goes to P prime, and then F of Q goes to Q prime, it should say equals, these are actually the same, then the distance from P to Q is equal to the distance from the mapped points P prime and Q prime. Okay. We also identified all of the isometries, and the reason why we were able to do that is because we knew that every isometry has an inverse. Minus 1 is the inverse, such that F of F to the minus 1 is the same as the identity, which does nothing in the mapping. And the important isometries that we identified were the translation. And you can uniquely identify every translation based on how it moves. So if point M goes to point P in this translation, then this uniquely identifies the translation. We also have rotations. And rotations go around a point. Again, they're unique. So if you say G takes like some point, let's say A, and that goes to B, then that uniquely identifies the rotation. You also need to have some kind of center point that you're rotating around. And finally, we have reflections R. Okay, and reflections go through a line. And these three, well, and of course you have the identity that's an isometry as well, trivial isometry. These four work together to produce any isometry that you'd like to have. So isometries are unique. Isometries have an inverse, and you can express any isometry as a composition of those three mappings. The other thing that we need to go is we need to go way back to the interlude on logic, and we need to revisit what it means when two sets equal. So if we have the set S is equal to the set S prime, what that means is S is a subset of S prime, and S prime is a subset of S. Okay? And so a subset, basically, if every point in S, if every item in S, it could be points, it could be other things. In this case, we're going to talk about points. If every item in S is in S prime, and if every item in S prime is in S, then we've proven that both sets are equal. All right, so these concepts are really important to this section, understanding congruence. Now, when you studied geometry, whenever you did, maybe in middle school or junior high or something like that, you probably started with some side angle side or some rules that circles that have the same radius are congruent, things like that. We're going to do it a little bit differently. We're going to define congruence, okay? We're going to say two sets, S and S prime, are congruent if there is some isometry my handwriting's terrible, F exists such that when you map all the points in S through F, you get S prime. These two sets are equal. Okay. We talked about in the last section, I believe, or the section before last, where we can apply isometries to entire sets of points and get a set of point back instead of just one point at a time. Okay. And so this is the basic rule. So that's why we need to know what it means for two sets to be equal. That's why we remembered how to identify all the unique isometries. We can find them all. And that's what we're going to do. Okay, so we're going to start with Theorem 7. Theorem 7 is pretty simple. It says two circles are congruent if their radius is the same. Okay? He words it slightly differently in the book. It means the same thing. And in order to prove this, we're going to first take the two circles. We're going to define A is the circle that has a radius of r centered on point O, and B is the circle, radius of r centered on O prime. I believe that's the notation he used. Yes, it is. Okay. So all we need to do is prove that there's some isometry F that will give us B when we put A into it. How do we do that? Well, let's think of an isometry that'll map these two sets on each other. We can think of a translation. So let's say T is a translation that takes O to O prime. Okay? And if we take T and apply that to some point P, where P is in A, so P is in an A, let's say Q is in B. Okay? If T of P gives you some point, all right, the question is, does that point, so some point P in A, does that point lie in B? Okay? And the answer is pretty simple. So let's take a look at the distance from the center O to point P. Because F is an isometry, then the distance should be the same because O is going to go to O prime and P is going to go to some point Q that happens to lie on B. You see the distance is preserved. What does that look like graphically? Well, let me just, let's use my fancy compass. I love this thing. Looks like my kids have been messing with it. Let's make it a little tighter here. Okay, let's draw a circle here. Kind of mess that up. Let's draw another circle over here. Let's do it this way because it's unscrewing the... All right, so that's probably not very visible. Let me get this guy in there. There we go. Hopefully you can see those. I think they're okay. So we're going to call this point here O, and this point here O prime. And obviously the distance between here and the edge is R, and the same thing over here. That distance is R. Okay? So when we take some point P, and then we translate that, we're going to get some point over here Q. Okay, so P is going to go to Q through that translation that maps O to O prime. And that is how we can see that for all the points P, it's going to be somewhere over here because the distance between O and P is preserved. And so the distance between points O prime and that new point is somewhere on that circle. But that's only half of proving that a set is equal to each other. We have to prove the other side too. So we have to prove that there exists some translation, and we're going to use the inverse translation that goes from O prime to O. And we're going to start with some point in B, Q. And indeed, because distance is preserved, it's going to give you some point in the other circle. This is circle A. This is the circle B. Okay? And so we proved through this and this that these sets are subsets of each other. Therefore, they're equal. All right? There is an exercise 2 in the back of the book that he mentions again and again. And I'm not going to give away the secrets here. It's not that terribly difficult. Exercise 2 says, suppose you have three sets, S, S prime, and S double prime. And we know that S is congruent with S prime, and S prime is congruent with S double prime. And it wants you to show that S is congruent with S double prime. Okay? And the other thing it wants you to show is that S prime is congruent with S. What this means is there's like a transitive property where if S is congruent with S prime and S prime is congruent with S double prime, then S is congruent with S double prime. And also that you can go backwards. So congruence is some kind of like equivalence, like if this number is equal to that number, then that number is equal to this number. It should be fairly trivial to do this, just using the simple math that you've already learned. But let's go on, let's do theorem 8. Theorem 8, in light of exercise 2, becomes a little bit simpler. Theorem 8 says any two segments of the same length are congruent. Okay, what does that look like? So I'm going to pull out my, I have a straight edge here that is difficult to pick up. Let's grab some colors. Blue and green seem to be nice. So I'm going to measure out, let's go from 1 to 4. Okay, that's one line segment. I'm going to measure out over here. I'm going to move it. I'm going to rotate it. Do you see how I started here, and then I moved it, and then I'm rotating it. Okay, and we're going to go from 1 to 4 again. Okay, these are two line segments. All right, let's give them a name. Let's say that this is PQ. This is point P. That's point Q. So this line segment is called PQ line segment. And this is point M here. And this is point N here. And so MN is a line segment. Okay. Now what we're going to do to prove this is we're going to grab our black marker. There we go. So we're going to say, first of all, the length of these, so proof. The length of MN and PQ are equal. That's a very strange way to write equal. These two lengths are the same, okay? So we have some translation T that'll map M to P. Okay? So that translation T, let's use a new color, this orange color. Okay? That translation moves point M to P. Okay? That's what that translation does. Is that enough? Because if we simply just move this line segment, it won't quite align. So we have to do something else. We have to additionally, we have to rotate with the rotation G, such that the rotation of this T of N is going to give you Q. And this is centered on P. Okay? All right. So T of N. So after we translate this, we're going to get a line segment. Let's use a new color. I'm covering up my colors. Let's use this nice purple. Okay. So we know that, and you'll have to be explicit about this if you're writing this out. And these things is impossible to pick up. There we go. So if we're going to translate M and N and just move it without rotating it, we're going to make the translation of M on P over there. There we go. And we get this. This is T of N. Okay. And so those aren't quite the same points yet, right? But then if we rotate it, because the distance is preserved here, the rotation, these two lie on the arc of a circle centered on point P. And so there is some rotation that'll take this point and move it to Q. And so it's a combination of these two. Okay. And so in order to prove this, then we're going to say the rotation of the translation of, I'm sorry, this is terribly wrong. Let's write that out differently. G of T, G composed with T, of some point, let's say all the points of Mn, will give you some set of points, right? All right. Let's do this. Let's write this out differently. So we're going to prove that for every point, let's say points A, where A is on Mn. Can you see that down there? Yeah. A is on Mn, and B is on PQ. Can you see that down there? Yeah. Okay. So for any point A on Mn, we're going to get a point that is going to be NPQ. So it's going to be equal some point B. Okay. But if we do the inverse of this, so we take the inverse G minus 1 of some point B, then we're going to get some point on Mn. Okay. So for any points, there's going to be this relationship where this is a subset of that, and that's a subset of this. And so we've proven that those two sets are equal. And that's how you do it. Now, if we're using the results from example 2, then it's rather trivial to say that S is going to be Mn. Then you can take S prime, which is going to be the translation of Mn, and then we're going to take S double prime, which is the rotation of the translation of Mn. Okay, and since this is equal to PQ, then we know that this is congruent with that, and that's congruent with that, so these two are congruent with each other. Pretty simple proof to do it that way, once you've figured out why exercise 2 works. Moving right along. Theorem 9. Theorem 9 is usually one of the first theorems you see, and typically they don't prove that this theorem is true. They just give it to you and say this is a good rule of thumb to use. Okay, the way theorem 9 works is we have two triangles. So we have triangle P, Q, M. And we have triangle P prime, Q prime, and M prime. We have two triangles. And these are triangles that are right triangles. And the right angle is on Q. So Q is the right angle, and Q prime. Okay. And the legs have the same distances. So the distance from P to Q is equal to the distance of P prime to Q prime. And the distance from Q to M is the same as the distance from Q prime to M prime. Okay. And if we have the right triangles centered on Q, and then the distances of the legs are the same, therefore, then, or whatever, these triangles are congruent. You might recognize this as the assumption RT, where we assume that two right triangles with the same lengths of legs are actually the same. Okay? So if you recognize that, congratulations. We're going to prove it now, so we don't need to rely on this assumption anymore. We can actually go back and prove it. And I don't believe we need to rely on the conclusions of RT to deduce RT, so we can actually prove it from scratch without assuming it at all. So the proof is left as an exercise to the reader. All right, so you should be able to fairly easily find a proof that this is the rather simple thing to do. And you might want to use the conclusions of exercise 2 to just find some congruent shape to triangle PQM. Maybe one of the points lines up with one of the points on the triangle, and then you rotate it. And you may need to do a flipping. Okay. For theorem 10, we're going to actually do a broader definition of something. And I have this weird piece of paper somehow caught in there. So let's throw that away and ask for our money back. So theorem 10 is a bit broader proof for triangles. This one says we have two triangles, PQM, and we have triangle P prime, Q prime, M prime. And so these triangles have legs of all the same length. So the distance from P to Q is the same as the distance from P to Q prime. So the corresponding legs are the same length. This is P to M is the same as the distance from P prime to M prime, and the distance from Q to M is the same as the distance from Q prime to M prime. Okay? And if this is the case, then they are congruent. This is the theorem. The proof is rather easy. It's going to look somewhat similar to the proof you're going to use previously. So now keep in mind that there's, like, here's a triangle. We can move this triangle, we can rotate it, but we can also do something that you can't do with line segments. We can flip it. Okay, so these triangles, as I move them, as I rotate them, as I flip them, they're all congruent. So let's walk through some proof. So first, we are going to find a translation such that P goes to P prime, I believe. Yes, P prime. So T is some translation. So that's one isometry. We found a congruent shape just by moving it. So that's equivalent to taking this triangle and moving it to line up. Let's draw two shapes here. I don't want to make them too big, so I'll just do this. I'll just go yoink, and then we'll do this. Yoink, and that's a right angle there. Yoink. Okay, that's one triangle, and over here let's do another. Let's actually flip it because it could be flipped. Yoink. Yoink, and I'm not even checking the distances. There, that one, and I'm terrible at drawing triangles, aren't I? And let's do another one over here just for fun. Yoink, yoink. Okay, pretend these are the same shape. They're not the same, but pretend that they're the same shape. Okay, they're the same congruence. They're same lengths and everything. They're not. I did a terrible job drawing these. I feel I should be fired for this. In fact, you should tell my manager, fill out the comment card, and get me removed from this position. Because I really don't do this very well. Okay, so we have those three triangles. Okay, so first we're going to do is we're going to pick one of these points, call it P, and then we're going to translate the triangle to line up with its corresponding side. Okay, so in this case you'd move over here. In this case you'd move this point over here. Okay, and then what you're going to do is you're going to find some rotation centered on P, such that the rotation will give you a will map Q to Q prime. Okay. Goes to Q prime. This looks awfully similar to just trying to get the line PQ. So let's say this is P, Q, and M, and let's say this one is P prime, Q prime, M prime. So what we've done so far is we've basically taken this line segment here, and we've moved it over here, and then we rotated it. So we've rotated the shape to map this line segment onto itself. right? So we've shown that this line segment and this line segment are congruent. And the same thing over here, we would have done the same thing. If this is P prime and if this was Q prime, then we would have, at this point, we would have a shape that looks like this. Let me draw with this light blue. So if we did this with one that isn't flipped, then we'd be done, right? But if it was flipped, we would have a triangle that looks like this, okay? So allow yourself to see why. So we take the P and we line it up over here, and then we have to rotate Q. So we rotate Q this way, and now this point M prime is sitting over here where it's not supposed to be. And so we have to add in the additional step of perhaps reflecting, such that the reflection of this, I'm sorry, this is the translated Q, not the Q itself. The reflection of the rotated translated M is equal to M prime. So we have to use some kind of reflection or not. Okay? So that's, in a nutshell, how you prove that. And at this point, there's a remark at the end. Let's talk about the remark. Remarks in mathematics is when you make some interesting observations that turn out to be very important, but he doesn't want you to do any much homework on it at all yet. So this remark has to do with what about, let's say, areas. Okay, we're going to talk about areas in the next section even more. So we dealt with line segments. We dealt with circles. We've dealt with triangle edges, not the triangle insides, but triangle edges. What do we do about areas? Well, we could imagine, right, that you take some triangle like this, and then you take and you map from one of these points to every point along the opposite leg. Okay, and that should convince you that that covers every single point inside the triangle. Okay. There is a little bit of a problem, though. If you are not convinced that this covers the entire shape of the triangle, then if you can imagine there's some point in here that isn't, like let's say we pick a random point here, this point here, let's call it M. Okay, and if we can't find a line that passes through M to the other side, then that would be a problem, right? But I think it should be fairly easy to prove that all the points will be covered inside of that region, that there's always a line that'll pass through any point that's on the inside of this region and intersect with the other line at the other side, okay? What if we wanted to do angles, right? So an angle, if you recall, is a region of space. We're not talking measures of angles, but regions of space. So in this case, this angle here, this is the region of space that we're talking about. This one could be this region of space, right? So everything beyond those two rays, right? So you could imagine constructing lines such that you take some point on one side, some point on the other side of these two things, and you can do any 2-point combinations, you know. And hopefully you can convince yourself that for every point in here, there's some line that passes from this line through that point to the other line, okay? And so you can cover every single point that way as well. The issue is that when you do this with areas, you can find a rule. You can say that for every, let's say that S is a region of a plane, so an area. Okay, and then we can say the area of S is equal to A. Okay, we haven't really talked about area. We're just making things up right now. Okay, the area of S is equal to A. So if we take some isometry and apply that to S, and then we get some congruent shape that's S prime, then we're going to say the area of S prime is also equal to A, that the area is equal when we preserve distance through these isometries. It seems reasonable, and it seems like it should work. There is a little bit of a problem. So we're able to show on the inside of the angle, but what about the outside region here, right? I kind of missed that here. I was meant to, like, how do you draw lines through each point, you know? Like, I imagine you can imagine that there's a line that goes off into infinity, a ray for each of these points, but it's a little bit problematic. But what is the area of this region? It's effectively infinite, isn't it? What's the area of this region? It's effectively infinite. So you have basically two infinities that equal each other, which doesn't make much sense. Okay. So that is where we're going. If you have a bounded region, so if you imagine that we put a circle around the center here, and we're only consider stuff inside the circle, then that's not an infinite region, right? So there's a little bit of a trick there. Even though the area is infinite, we will say that the regions are congruent. All right. Anyway, exercises are fun. They're not too hard. I hope you have fun with them. Take care and bye-bye. Hey everybody, thanks for watching. This is part of a series on Sergey Lang's Basic Mathematics. You can catch the playlist over here, and you can find out how to support my channel over here. Thanks so much. Have a great day. Bye-bye.